That's somebody who shoots, right?
Some of both. Some of both. Our job's kind of dirty because we have to do both. We have to play like the big man and the guards.
Okay. All right. Well, good. Keep us posted. Are you on a winning team?
Yeah, we made first round nationals last year.
Wow. Y'all may want to get autographs. I'll go find your test and tear your name off. All right. Are we ready? Okay. Welcome back, everybody, to Math 107. This is the first lecture after the test, although we started section 3.2 before the test. We were working on polynomial functions, chapter 3, section 2. I just want to briefly go back and quickly talk through what we did. We learned to identify a polynomial function. Okay, so we're going to have a y equals. What has to be true about the exponents on the variable for a polynomial function? The exponents, what do they have to be?
Real numbers.
Real numbers? Is that right, everybody? Real numbers?
Whole numbers.
Whole numbers, that's a much better word. Your exponents on x are 0, 1, 2, 3, 4, 5. Real number could be like a fraction, a half. Could be like square root of 3. Okay, could be, a real number could be negative 17. Okay, so your exponents can only be non-negative integers. Non-negative integers. Non-negative means it could be 0, and an integer would be 0, 1, 2, 3, 4, 5. And we used to call those whole numbers. Okay? Alrighty. So we learned to identify polynomial functions. So it's got to be x to some power, not 1 over x, not a square root with the x in it. And then we learned last time also to identify the degree of a polynomial function. So if you have a polynomial function, how do you determine the degree? Okay, the term with the highest exponent, and that highest exponent is the degree. How do you get a 0 degree polynomial? 0 degree polynomial. Give me an example.
If the exponent is 0.
Okay, if you have an x to 0, so you might have a number like y equals 7. You could write that as y equals 7x to the 0, so that would be a 0 degree polynomial. Okay? All right. Then the next thing we did was we started talking about the power function, which is a special polynomial function. And this is the bottom of page 319. We were just going to look at a power function so that we could start looking at the behavior of the graph. What was the shape? And we talked about when the exponent was even and when the exponent was odd. Okay. So let's see, impress me and tell me what you remember. If we have an x to an even power, like x squared, x to the 4th, x to the 6th, x to the 8th, what do we know about the ends of the graph? Okay, they go in the same direction, and if the a is positive, they both go up, and if the a is negative, both the ends go down. So when you have a power function, which is just that one term, ax to the n. If n is even, you know the graph's going to look a whole lot like a parabola. Okay, so how is the graph of y equals x squared and the graph of y equals x to the 10th? How do they compare? Y equals x squared. What is the shape? How's the shape different? Y equals x squared and y equals x to the 10th. Go ahead. They both look like this, but what happens? Well, you first, before you got to the I don't know part. Okay. All right. What do you think, Sarah?
What was that? Y to
The graph between y equals x squared and y equals x to the 10th, if you were going to graph those, how are they going to look a little different? I mean, they're both going to go like this on the ends, but where's...
x to the 10. 10 is an even number, correct?
Right. And x squared, 2 is an even number.
So they're both parabolas.
Right. They both look like a parabola, but there's a little something different about their shape.
10 raises up faster.
Okay, x to the 10th is going to go up a lot faster when? After x equals 1 and negative 1. Remember, on each side of 1 and negative 1. Aaron, what were you going to say?
I was going to say the same thing.
Okay, now there's a little place that things look a little different. What happens between negative 1 and 1?
It The x to the squared goes up faster.
All right, because you're exactly between -1 and 1, y equals x to the 10th is going to be a little flatter, and underneath y equals x squared, because you're thinking of a number like a half being squared versus a half being to the 10th. So y equals x to the 10th, it's going to be kind of flat between -1 and 1 along the x-axis, between -1 and 1, and then all of a sudden it's going to go up really fast, where y equals x squared is going to go up a little higher between -1 and 1, but then it goes up slower. Okay, everybody remember that from the graph? All right, what does the graph of y equals x cubed, x to the 5th, x to the 7th look like?
One up and one down.
All right, so it looks like, I better do it this way, like this, oh wait, backwards, like this and like this, right? Okay, and they're still going to have that little same shape, except it's going to be a little flattened out between -1 and 1, the higher the exponent is, and then the higher the exponent, then it goes up faster and drops quicker. Okay, everybody good? So they're going opposite directions. Now if the a in front of the x cubed, x to the 5th, or whatever is negative, then it's just going to reflect about the y-axis. It looked like a reflection about the y. It's also a reflection about the x-axis. Okay? All right, so let me flip back where we left off and just quickly catch us up. All right. The last example that we did in class at the last tape, and I've lost the sheet, the graph. What did I do with it? Here it is. Okay, the last thing we were looking at was on page 331, and we looked at problem number 33. I think we picked an even one, an even function to graph. We had gone beyond the power function and we were just doing transformations. This looked a whole lot like x to the 4th, the power function x to the 4th, which was even, which you knew the ends were going to go in the same direction. Then, of course, because there was a positive 2 there, they were going to go up. The 2 in front of the x4 to the 4 told me that was a vertical stretch by a factor. Factor is multiplied, factor of 2. Then the +1, you told me that was a vertical shift up of 1. And then this x +1 inside parentheses, you told me it was a horizontal shift to the left of 1. And I think we went through all of this on the last tape. And where is the final one? Right here. Right here. There. So that's where we were when we left off last time. Okay? All right, so now we want to go back to page 331. This was an even power. Let's pick one of the same problems. Let you pick one. That's an odd power. So I'm on page 331 for transformations. And we were looking between problems 23 and 34. And we just did an x to the 4th. Let's pick one that's an x to the 5th. Which one would you guys like to do? You name it.
35.
Okay, I'm hearing 31, and the next one I heard was 35. So let's go unison. Which one, 31 or 35? You name it.
31.
35.
All right, Democratic classroom, vote real fast. Raise your hand for 31. 1, 2, 3, 4, 5. Well, I believe that's going to do it. All right, so which one did I say, 31? Okay, so we're going to look at number 31. Okay, number 31, page 331. And we have f of x equals x minus 1 to the 5th plus 2. And you guys on your test were very good at discussing your graph, listing your steps, and one of the reasons I pushed it so much is because I knew this was coming up, and then we're going to do rational functions, and then we're going to do exponential and log functions. So that same process is going to continue through. All right, so remind me what the basic function is here. Y equals x to the 5th. All right, now, what does the plus 2 tell me I'm going to do? Vertical shift up 2. And what does and that's not a factor of 2. Some of you on your test wrote vertical shift factor of 2. Factor means multiplied. That meant the y values were multiplied by 2, but no, this says the y values are added
So
2 are added. So if you wrote factor, then that was incorrect. Factor means multiplication.
But it's a vertical shift up 2 units.
Right. Vertical shift up of 2 units. Okay, and what does this x minus 1 tell you you're going to do?
Horizontal shift right.
Horizontal shift. And it's going to go right because it always looks opposite of what it is. When you're working with the horizontal, right of 1 unit. Okay? All right, what would need to be here if it was a vertical factor of 3? Vertical factor of 3. 3 would have to go right in here. Okay? What about a horizontal shift a horizontal stretch or compression? It would have to be with the x. Okay, a factor with the x. Okay. So here we go. Let's sketch the graph. Hey, graph it while I'm doing it, and then I'll let you guys help me out. All right, let's see how it's going. I bet it's going very well. All right, the graph of y equals x to the 5th. We already know that's an odd power. By the way, what kind of function is this one right here called? It's called a, starts with P.
Polynomial.
It is a polynomial function, and this is a special case called a power function. Okay? And we already know that because the coefficient from the x is positive 1, we know the graph's just going to look like this, basically. All right, so let's see if I can't draw this. It's going to go through 0, 0, 1, 1. These are solid dots. -1, -1. Now, because it's at x to the 5th, it's going to be a little flatter between 0 and 1. Of course, you don't want to plot all these points, but it's a little flatter than y equals x cubed between 0 and 1 and 0 and -1. A little flatter towards the x-axis. All right, than if it were just an x cubed. And then after 1, it's going to go up a lot faster than x cubed and go down a lot faster than x cubed. Okay, so this is y equals x to the 5th. And again, you could just plot some points if you would feel better about putting in a half, -1/2. All right, so there's y equals x to the 5th. Okay, then you told me we're going to do a shift up of 2 units. All right, so 1, 1, 0, 0, -1, -1. So we're going to shift up 2 units. That up means work with the y's. We're going to add 2 to each y value. Is that what everybody did? So we go 0, 2, 1, 3. Same old graph. It's just been shifted up. And -1, 1. So this is 1, 3, 0, 2, and we have negative 1, 1. Same graph, just pulled up. So this is y equals x to the 5th plus 2. Okay? All right, and then the next thing you told me, we're going to do a horizontal shift to the right of 1. So if we're going this way 1 unit, what am I going to add 1 to? The x values. So we're going to add 1 to the x values because that's horizontal. 1 to the x values, 1 to the x values. So 1 plus 1 is 2, so now we're going to have the point 2, 3, which is coming over a unit of 1. This is 2, 3. This is going to be 1, 2. And this is going to be 0, 1. So the graph is going to come over, oops, make that dot bigger, like this. Got my units off a little bit, like this. This is going to be the graph of y equals x minus 1 to the 5th plus 2. Okay, this point right in here is 0, 1. And let's just double check those points. If you let x be 2, 2 minus 1 is 1, 1 to the 5th is 1, 1 plus 2 is 3. Check. Let x be 1, you got 0 plus 2 is 2. Check. And you let x be 0, negative 1 to the 5th is negative 1, negative 1 plus 2 is positive 1. We are good, good, good. Does everybody's work look like that? All right, let me ask you a question. As x approaches infinity, what does the y value approach? As x gets really big, what are the y values getting close to?
Infinity.
Infinity. Who remembers from, I think I wrote this last lecture, how do I write this as a limit?
That's
The limit as x approaches infinity of this thing, which is x minus 1 to the 5th plus 2. So this says, as x approaches infinity, this y value, this is your function y, is going to, and then when you're working with limits, you actually say equals to, but it really means approach, is going to approach infinity. The limit is infinity, which you can never touch, but you use it equal to. This is the way it's said in most pre-calculus courses. Then you get to calculus and they use that concept limit. Some pre-calculus courses probably do limits also. All right, everybody good? What about as x approaches negative infinity? What does the y value approach? As x approaches negative infinity, what's happening to those y values?
Negative infinity.
They're still headed in the direction. Ooh, that was a bad. That's a negative infinity. So we might write, get ready for calculus, the limit as x heads in the direction of negative infinity. I'm just going to write f of x here. That's my function. Okay. Whatever that function is, this says as x gets real close to negative infinity, what does the y value get real close to? And everybody writes negative infinity. It means you can't reach it, but it's just going to head in that direction. Okay, what is the domain for this function, by the way? Domain. Domain.
Infinity.
Okay, everybody in unison says?
Infinity to negative.
No number.
All real numbers, right. When do you have to worry about domains? When you've got square roots or something, right, because you can only take the square root of a 0 or bigger, or if you've got a denominator, you can't divide by 0. So if it's a good old polynomial, for every polynomial, the domain's going to be all real numbers. What's your range here? What's your y values? All real numbers. All y values are taken care of. All right, are we good with power functions? Power functions? All right, so we're working on polynomials, and we just looked at the simplest type of power functions. Simplest types of power functions, but we know all polynomial functions are not little power functions. So before we continue, we have a term that we want to make sure we're good at, And and this is actually objective 3 in your textbook. But before I direct you there, I want you guys to tell me what zeros of the function y equal f of x. What does that mean? Yes. This means zeros of the function. It means what makes the y values 0. Solve for x. So on the graph, it is exactly what you said it is. It is the x-intercepts. Okay? Keywords you're going to hear forever and ever. Very important in your calculus, your pre-calculus class. The term zeros of the function means what makes the value of the function 0. It means solve for the x where the function is 0. Okay, we've already had a little experience with that when we were working with quadratics. So before I head to the textbook, I want us just back up and review a second. When I gave you a function like f of x equals x squared minus x minus 6, we know that good old quadratic. You know, it's a parabola opening up, all this stuff. So let me change the words. Let me ask you for the zeros of this function. If I ask you for the zeros of this quadratic function, what are you going to do, everybody? Set it equal to 0 and solve. So it's like you're finding your x-intercepts. Okay, so we're going to set this equal to 0 to solve. How are you going to solve a quadratic? You're going to go to the quadratic formula because you hate to do the big F word. What else can you do?
Factors.
Do the big F. Right. Factors. X minus 3, x plus 2 equals 0. And then you use the rule that a times b equals 0. When you have two factors, factors means things are multiplied together, factor, multiplication. When you have two factors multiplied together, then you set each factor equal to 0 and solved. Okay? So in our example, we've been basically saying 3 and negative 2 are the x-intercepts. But we can say 3 and negative 2 are the zeros of the function. You'll be wondering, why am I making such a big deal over this? All right. Now, notice, this is what I want you to notice. If 3 is a 0 of the function, if we work our way back up this problem, notice that x minus 3, x minus the 0 is a factor. So if 3 is a 0 of a function, then x minus 3 is a factor. Notice that negative 2 is a 0. X minus a negative 2, x minus that negative 2, x minus a negative 2 is plus 2. X minus a negative 2, which is equal to x plus 2, is a factor. Okay, so where are we headed with this? Given a polynomial function, if we know the zeros, then we know how to write the factors. Or if we're given the factors, we can identify the zeros. By the way, this is called a linear factor. Why is x minus 3 called linear?
The line.
It's a x to the first, right? It doesn't have an x square. Anything that's like mx plus b is linear. So it's a linear factor. Suppose it came out to be something like x squared plus 3. What kind of factor would you call that? X squared plus 3? Quadratic, and that would be called what is called an irreducible quadratic, meaning it couldn't be factored further under the set of real numbers. All right, but let's go back to what we were talking about. We're trying to get into polynomials that are have more than just 1 or 2 zeros. Zeros of the function. If we know the zeros, then we would know how to come back and get the factors. If we know the factors, then we know the zeros. All right, so where I'm trying to send you to is page 323 in your book. I hope you're wearing your book out. You paid a lot of money for it, so you need to be using it. Didn't you pay a lot of money? Oh, yeah. Expensive books. All right. If f is a polynomial function, all right, I know that I've asked you this already, but I'm trying to make sure it goes to your long-term memory. How do you look at an equation and tell it's a polynomial function?
A non-negative integers.
All right, your exponents are non-negative integers. All right, you couldn't have like a x to the negative 3 in your equation, and you couldn't have like a square root of x in it. It's just got to be x to the 0, x to the first, x squared, x cubed, x whatever. All right, so you recognize a polynomial function, and r is a real number for which the value of the function at r equals 0. You're setting your function equal to 0. Remember the example we just did? We set our x squared minus x minus 6 equal to 0. So basically, let me back up on here. Let me do this in a different color. Here was our function. It's basically saying f of 3 is 0, because that's the value you put in. It's going to make that function equal to 0. Or f of negative 2 is 0. We found those to be zeros. That's what that means. Do you see how that's relating to the definition that we're working on right now? Okay. So, if r is a real number for which the value of the function at that r equals 0, then r, that little r there, is called a 0 of f, 0 of the function. Another thing you can call it is a root of the function. In our math department at State, we're really big on calling them zeros of the function. Okay, so that's probably all you'll ever hear me say. All right, so that value r that makes that function 0 is called the 0 of the function. Now, if r is a 0 of the function, and we're only working with real numbers right now, then r is an x-intercept of the graph. You already knew that, right? Because we set the y value equal to 0. But the part that it's new that we're stressing is that x minus r then is a factor of f. Okay? X minus r is a factor of f. Well, if you know a 0, then you can go back and say x minus that 0 must be a factor. All right. Let's put it all together on the next example. Example. The instructions would be find the zeros of f of x equals 3x squared minus 3x minus 18. Find the zeros of the function 3x squared minus 3x minus 18. All right, you jump on it and go for it. What are you getting?
-2 and 3.
-2 and 3. X equals -2, X equals 3. Well, that sounds like to me those were the same zeros when we had x squared minus x minus 6, but that polynomial function is different than this one. All right, what I'm hoping that you did was you said f of x equals, and you saw that 3 was a common factor in all terms. So you factored out a 3. Oops, 6. Factored out a 3, and then you had 3 times x minus 3, x plus 2. All right, so I've kept the same function. I just factored out a 3 first, and so when you then set that equal to 0, you get x equal 3, x equal -2. So how is this function different from the function that we did back here? How's it different?
The A wasn't.
The A is 3, which means that it's going to be a stretched by a vertical factor of 3. Stretched by a vertical factor of 3. Okay, it's going to be stretched. All right, now here's my point that I was trying to get to. Everybody good so far? My point is, I want to turn the problem around. Given the zeros of a polynomial function of degree 2, given the zeros of a polynomial function of degree 2, the zeros are -2 and 3, find the function. Find the function. How are you going to write the formula for the function for the zeros of a polynomial of degree 2? Because I just showed you there were 2 possibilities here. Actually, would you see there are more than 2 possibilities if I multiplied through by a 4? If I took this original function and multiplied through by 4, or multiplied by 10, or -7, or whatever, they would all still have the same zeros. All right, so we just looked at the definition over here in the book. If -2 is a 0, what is a factor? X plus 2. If 3 is a 0, another factor is x minus 3. But how do you represent all polynomial functions with these zeros? Does that sound like a trick question? You just put a little a right here, where a is a real number, where a is a real number. This represents all functions, all polynomial functions that have zeros -2 and 3. Okay? All right. I'm going to go a step further on this problem. Everybody with me? Go a step further. Find the function that also contains the point 1. I bet I'll make up something too weird here. It's always scary to make up something when you hadn't really practiced it out first. All right, so I may be all wrong here, but I'm going to say contains the point 1, 8. All right, so what's happened is I want a particular polynomial function. It's going to pass through the x-axis at -2 and 3, and that curve is also going to pass through the point 1, 8. Right?
1 equals 8 plus 2 and 8 minus 3.
Okay, now which one goes for x and which one goes for y?
I mean, you plug 1 to x. And
1.
8 next to h y.
You are so perfect. Once you get this far, then this represents every polynomial function that has zeros -2 and 3, but you want the particular one that goes through the point 1, 8, so that information allows you to go back and solve for a. You are very good. So y is equal to 8 a times, and in the place of x, I'm going to put a 1. 1 plus 2, 1 minus 3. And see, now I have an equation with just one unknown. So 8 equals a. 1 plus 2 is 3. 1 minus 3 is negative 2. So 3 times negative 2 is negative 6. So a then is equal to 8 divided by negative 6, or if you wanted to reduce that, that would be what, negative 4/3? So therefore, if I had the rest of the question to my problem, my new function that has the zeros negative 2 and 3 and passes through that point is f of x equals negative 4/3 x plus 2 x minus 3. And if you didn't have anything else to do, you could expand the product and see the whole polynomial, but otherwise you just quit right there and life is great. Okay?
Wouldn't it be positive?
8 divided by negative 6 is negative 4/3. Positive divided by negative, right? I'd have to have a negative divided by a negative to be a negative. Did I answer your question?
Yeah.
All right, everybody good? All right, next thing that I'm trying to illustrate to you about zeros. All right, we'll go back in the book and I'll make sure I'm covering every single thing that I need to do. Suppose that you were asked to find the zeros of x squared plus 4x plus 4. I'm using some simple examples here to illustrate my point. All right, we want to find the zeros. Find the zeros. Okay, so I know everybody immediately is going to, except you're going to jump on the quadratic formula. All right, we're going to set the function equal to 0. And how does this factor?
X plus 2 x plus 2.
All right, this is a perfect square trinomial, and it factors to x plus 2 quantity squared. X plus 2 times x plus 2. All right, this is a second degree polynomial. I am expecting 2 zeros, but it doesn't mean the 2 zeros have to be distinct, okay? So you would basically be saying x plus 2, I mean, you really don't do this, but you say x plus 2 is 0, x plus 2 is 0, x equals negative 2, x equals negative 2, basically. But we really only have one distinct 0. So what we say is, this is what we say. What do you say? Yes, you got the right word. Negative 2 is a 0 of multiplicity 2. The 2 being because it's twice negative 2. So if you had a function f of x equals x plus 2 quantity to the 10th, you would say negative 2 is a 0 of what multiplicity?
10.
Multiplicity 10. It just means negative 2, negative 2, negative 2, negative 2. So whatever the power is, you have that many zeros, but they may not all be distinct. Everybody got it? Well, let's see. I feel like you do. Any questions? We're going to go to the book, work an exercise. Okay, I'm on page 331. 331. And we're just going to pick a problem here. Any of them that look good. Let's just go to number 49 because it happens to be in the middle of the page. All right, this is a polynomial function. Just happens to be factored for me. First of all, I'd like for you to tell me what the degree of this polynomial is.
2.
That means you'd have to like mentally multiply everything out, but just stay focused on the term of highest power.
4.
All right, now if you square x squared plus 4, x squared plus 4 times x squared plus 4 is going to give you an x to the 4th power. And this is, when you multiply that out, that's going to be an x squared. So you're going to be multiplying an x squared times a x to the 4th. So you're going to have a x to the 6. Remember your properties of exponents, x squared times x to the fourth. The bases are the same, so you add your exponents. Okay? All right, so let's make sure you mentally, visually got that again. X squared, can we zoom a little bit? There we go. If you multiply x squared plus 4 squared, I'm just staying focused on the x terms. X squared times x squared is going to be x to the fourth. X squared times x squared is x to the fourth. And if you square this thing over here, you're going to get an x squared. So you basically have an x squared times an x to the fourth, which is going to be an x to the sixth. Everybody follow that? Let's try another one real fast. We'll still come back to problem number 49. What about number 46? What's the degree of that function, that polynomial function?
4.
Yeah, that's going to give you an x cubed, and then you'd be multiplying times the x to the first, and that would be an x to the fourth. What about number 47? What's the degree of this polynomial function?
5.
5.
X to the fifth. Y'all are doing good, good, good. Let me see if I can find a hard one. Anybody see a hard one? That's too bad. No hards.
53.
Surely there must be a hard one somewhere. Oh, let's try 53. Maybe that one's kind of hard. Actually, that one's not too hard.
That's all.
What do you think that one is?
6.
All right, that's going to be an x to the fourth times an x squared. All right, I guess no hard ones. Looking for a hard one.
55.
No hards. Okay. All right, so we're back on 49 now.
So odd.
Okay, so this, everybody agrees now, is a x to the sixth power. Okay. Now, what are the zeros? All I'm asking for, what are the zeros of this polynomial function? And you would say
Negative 1/2.
negative 1/2.
Negative 4.
2. 2.
Okay, I'm looking for real zeros. If I put a 2 in for x squared there, is that going to make that factor 0?
No.
No. So really, you only have one real zero. Real number 0. Only one real number 0. Now, this book does not start talking about complex zeros until we get over into section like 3.6 or 7, somewhere like that. But x squared plus 4 does not have any real zeros, because if you do x squared equals negative 4, x is equal to plus or minus 2i. So we only have one real zero here, and that's negative 1/2. What would you say the multiplicity of that zero is? 2. So you have one real zero, a multiplicity 2. That tells you that this 6-degree polynomial is going to cross the x-axis how many times?
2.
Twice. Or it's going to at least touch the x-axis twice, because you got 2 x-intercept. I'm sorry, once. Once, because it's of multiplicity 2. It's the same one of multiplicity 2. Okay, so in this case, it's actually just going to touch it and run around. I'm going to talk to you about that in a second. Let's back up to an easier one, gets everything straight. Number 48. What are my zeros, real zeros?
3.
3 and negative 4. All right, the degree of this polynomial is 4, fourth degree polynomial. So you could have at most 4 distinct zeros. At most 4 distinct. But you only have 2 factors here, so we say x equal to 3 is just a multiplicity 1. X equal negative 4 is a multiplicity 3. How many times is this going to touch or cross the x-axis? Twice, and that's going to be at 3 and negative 4. 3 and negative 4. Okay? Has everybody got it? Oh, number 55. I like number 55. Yes?
I don't get why you don't have the 4 in 49 and you have the 4 in 48.
In 48, you would say x plus 4 equals 0, x equals negative 4. Okay, in 49, you would say x squared plus 4 equals 0, x squared equals negative 4, and then you'd be trying to take square root of negative 4, and that's not a real number. Thank you for asking. Is that good? Everybody good? All right. Which one? Oh, 55. I liked 55. What are the zeros in number 55?
0 and...
None.
That's not real.
Yeah.
Oh wait, it is 2.
What do you think?
Square root of 2.
Square root 2.
You are good.
Yeah.
Yes. All right, let's do number 55. That's a good problem. f of x equals minus 2x squared times x squared minus 2. All right, this is a fourth degree polynomial function. What do you know about the ends of the graph of a fourth degree polynomial function?
Okay. Both going in the same direction.
Both going in the same direction, and you actually told me the direction with your fingers, but you probably weren't on video. So what direction did you send them?
Down.
Down, because you got a negative 2 there. So it's a fourth degree headed down. The ends are headed down. Okay, zeros. This is already factored for, so you could say like minus 2x squared equals 0. You actually didn't even have to put the negative 2 there, because negative 2 can never be 0 anyway. And x squared minus 2 equals 0. So this means exactly what you told me. X squared is 0. And then when we solve this, you get x squared equals positive 2. And then how do you solve for x?
Square root of both sides.
Square root of both sides. What principle are we using that I've mentioned several times? It's called the square root principle. And what have you got to be careful when you take the square root of this 2?
Plus or minus.
Plus or minus square root of 2. So what are my, everybody good? What are my distinct zeros? 0, positive square root of 2, and negative square root of 2. So this graph, if you were going to graph it, is either going to touch or cross through the x-axis 3 places, 0, 2, and negative 2. What would you say the multiplicity of the 0 is? Multiplicity of the 0. 2. 0 is a 0 of multiplicity 2. Does that make sense? And positive square root of 2 is a 0 of multiplicity 1, and negative square root of 2 is multiplicity 1. Okay? It's important to know about the multiplicity because that will determine whether the graph actually goes through the x-axis or if it touches the x-axis and turns around. Yes?
The way I learned it was, you basically took a number line and you had all the values on the number line, and if it had an even multiplicity, you just like graphed it through that number line, and if it had even multiplicity, you bounced off of it, and if it had an odd multiplicity, you went through it.
You are exactly right, and that is the part that we're headed to in the book. All right, that is exactly correct. So we are on page 325. You just heard a verbal summary of what we were saying. And it has to do with the multiplicity of the 0. We're heading in the direction of graphing these polynomials based on their zeros, their multiplicities. That's where we're going. All right. If R is a 0 of even multiplicity, so like in this example, 0 is of multiplicity 2, so it is a even multiplicity. Then what it says is the sign of the function does not change from one side of R to the other side. In other words, it's just going to touch the R-axis and the x-axis and turn around. It's not going to cross through, and that's exactly what Aaron just said. So if the curve was coming down to the x-axis and it's of multiplicity 2, 4, 6, or 8, it's just going to turn around and go back once it touches the x-axis. All right, if R is a 0 of odd multiplicity, then it's actually going to cross through the x-axis because the sign will change on both sides. So therefore, when we get ready to sketch a graph, whenever we have an even multiplicity, we'll be able to quickly sketch it because it's just going to turn around and bounce back on whatever side it is. And if it's odd, then we will go right on through. Okay? And let's go to one more little theorem down at the bottom of the page. It's got a little calculus symbol by it. What it's trying to do is talk about what they call turning points of the graph. Now, turning points are really where your relative max or mins occur. That's all it is. Turning points got to turn around, come the other way. So you know you got a relative max or min there. All right. So it says if f is a polynomial function of degree n, then the function will have at most n turning points. n minus 1 turning points, relative max or mins. All right, you already knew a whole bunch about this because, let me just sort of illustrate that. When you had y equals x squared, didn't your graph look like this? It had one turning point. When you had y equals, I wanted to tell you something else. Oops. X cubed, it says at most one turning point. Actually, y equals x cubed didn't really have a turning point where it was a relative max or min. So it says it would have at most 3 turning points. This particular power function really has no turning points because it's not turning around going the other way. All right. If you have an x to the 5th polynomial with a lot of zeros in there, it could have at most 4 relative max and min points. Okay, again, the words are f has at most n minus 1 turning points. All right, I have just got the signal that we're about to run out of time on this one, so we're going to start back and finishing this section 3.2, and then we will pick up with section 3.3 in the next lecture. Okay? All right, take a break, everybody, and enjoy. I won't have a test made up by Monday.
Oh, okay. Just let me know when I can do it.
Okay.
I'll do it.
All righty, we are back, ready to go. We're on lecture 8B. And we did not finish section 3.2, polynomials. We were talking about turning points, and I think I was sort of confusing the issue at the end, which sometimes when we're finishing up a tape and I'm trying to get something said, that may happen. So I have some examples to work on turning points. Then I will want to also include, we've talked about in behavior. I want to flip through and make sure we're good, work a couple problems out of the exercises. Hopefully do all that in about 15 or 20 minutes, and then move into section 3.3, rational functions. We actually need to be on schedule and finishing rational functions today. All right, so at the end of the last lecture, we were talking about those turning points when you have a polynomial function, and we're on page 325. If f is a polynomial function of degree n, then f has at most n minus 1 turning points. So I have an example that I'm going to build on to illustrate what I'm talking about. So this is our example, and we want to sketch y equals x times x minus 3 times x plus 2. Now, this is a course where we aren't using calculators to identify the absolute max and minimum points and stuff like that. You'll use derivatives in calculus for that. We're just trying to get a visual of what the shape of the graph is, talk about the end behaviors, and also talk about the zeros and stuff like that. So your book will say use a graphing utility to find the minimum and maximum point. You'll use derivatives next semester in your calculus class to do that.
I got a question actually about derivatives and stuff. Like some of the homework that we've been doing on WebAssign, it seems like some of the questions were easier to answer using derivatives instead of...
Well, yeah. Derivatives are a nice little tool for quickly finding max and min points, but you don't really get derivatives till calculus. So in here, we're really just trying to get the shape of the graphs, have some understanding before you get to the next little tool.
Okay.
Yeah, absolutely. That's one reason when we sketch one of these, I'm not going to make a big deal about what is the relative max or min or something like that. Okay, so let's just get going. What is the degree of my polynomial function here? Degree.
3.
Third degree. It's of degree 3. What are my zeros of this function?
3 and -2,
3, -2,
and I don't know, 0. No.
and 0. Where'd that 0 come from, everybody?
Yeah.
I've got 3 factors.
X to the 0.
So you have x equals 0, x minus 3 equals 0, and x plus 2 equal to 0. My advice to you in your notes is to make a big circle, star, whatever about that 0. I can't tell you how many people miss that on a test if you just have the factor x. Each factor is set equal to 0. Don't miss that, okay? Zeros are x-intercepts. That's where it's going to touch the x-axis. What is my y-intercept here? Y-intercept. When you let x be 0, the y value is 0, right, in this case. All right, we're going to sketch the graph. And the way I like to sketch, and this is not a perfect sketch, because we don't know, we're not going to figure out all those y values. We're just kind of looking at the shape. Oh, by the way, this is a third degree polynomial function. So we know the end behavior, because it's going to look very close to, this end behavior means, like, if you looked at this from 2 or 3 miles away, what does it look like the very ends of the graph is doing? Okay, it's a third degree, so in the long run, when you're way away, you're going to see the ends of the graphs doing what? Opposite direction or same direction? Opposite direction. So it's going to be going up as x gets big, and it's going to be going down. How do I know it's going to be going up as x gets really big and down?
X is positive.
The leading coefficient for your x cubed term is positive here, if you were multiplying that out. That is very good. All right, we know how to sketch this graph very quickly. We're going to plot 0, 0. We have a 0 at 3, and we have a 0 at -2. Okay, you just told me the end behavior is when x is bigger than 3, this thing's got to be going in the positive direction, and when x is less than -2, it's got to be going down, right? Because it looks a whole lot like a x cubed on the ends. Okay, now I like to do what's called a little sign chart. I like to do what is called a little sign chart here. And a sign chart just says, I'm going to break up this graph when x is bigger than 3, between the zeros here. When x is between 0 and 3, when x is between -2 and 0, and when x is less than -2. I'm going to jump all around my zeros because this curve is a continuous curve. There's no place it's undefined. There's no division by 0. So I'm going to have a smooth curve. And when it hits a 0 on either side of it, it's got to be above the x-axis or below. So when I say sign, I mean, is the y value positive or the y value negative in those areas? If y is positive, we're above the x-axis, right? And if y is negative, we're below the x-axis. All right, so let's start where we already know the answer and just kind of show that. If we pick a number bigger than 3, for any value bigger than 3, the curve cannot come back and cross the x-axis, or we would have found another 0, right? So on the other side of 3, it's always got to be above the x-axis or below. And you've already told me above because it looks like an x cubed. Well, any number I pick bigger than 3, such as 10. If I put a 10 in for x here, is the sign, meaning positive or negative, is the sign, S-I-G-N, positive or negative? So if you put a 10 in each of these factors and multiplied it together, you'd have a positive, because 10 minus 3 is 7, and positive, because 10 plus 2 is positive. So if you multiply 3 positives together, you get positive. So you know your graph is curving like this when x is bigger than 3. Okay, let's pick between 0 and 3. Any number, because either the entire graph is below or above, because the only places it's touching the x-axis is between 0 and 3. It's 0 and 3. So pick an easy number such as 1. Okay, if I put a 1 in for x, that's positive. What about this factor? Negative. And a 1 in for this factor is positive. So a positive times a negative times a positive is a negative. That means all the y values are negative. So all we have to do is just drop our little curve down. Now you'll notice that I didn't indicate any points here on the any units on the y-axis because I really don't know how far down it goes. You can use derivatives in calculus and you'll be able to find that. Okay? All right. Now we want to go to the little interval between -2 and 0. Easy one would be -1. Now you realize when we're plugging this in, all we have to do is keep up with how many negatives we have, because if we multiply an even number of negatives, it's positive. If we multiply an odd number of negatives, it's negative. So if I put a -1 in here, this factor is negative. There's 1. If you put a -1 in for x here, this factor is negative. So there's 2 of them. Put a -1 in this factor, that is positive. So I've got 2 negative factors multiplying together, which means this entire y value is negative times a negative is a positive. Positive times a positive is positive. So your y values are positive. So we'll just take this and send it around right here. Again, I don't know how high up that's going. I don't know what the max is. All right, and you had already told me when in the end, as x gets really small, this thing's got to be going down because of the end behavior of the graph. But we'll just put in a number like -5. Okay, if I put in a -5 for x, that's a negative. -5 minus 3, that's negative. -5 plus 2 is negative. I have 3 negatives multiplied together, so that is negative. So the graph's going to go like this. Okay? Now, this is a basic shape of this third-degree polynomial function. The book said if we have a third-degree polynomial function, the function will have at most 3 minus 1, and in this case, 2 turning points. And in this case, we do have 2 turning points here where the graph turns around. We used to call those humps. It has 2 humps. Okay? All right, is that good so far? All right, now I'm going to change the problem, and let's look at y equals x times x plus 2 squared. All right, I'm going to really work over our third-degree polynomial to illustrate my point. All right, this is, oh, I didn't mean to tell you it was a third degree. Let's let everybody feel good. What's the degree of this polynomial function? Y'all are good. Okay, third degree polynomial function. Anybody not seeing why that's a third degree? If you square x plus 2 times x plus 2 is going to give you an x squared term. X squared times x is x to the third. Okay. All right, what are my zeros? 0 and -2. What do we say about the multiplicity of -2? -2 is a 0 of multiplicity 2, because I've got a square on that particular factor. Okay? And we still have a y-intercept of 0 here. All right?
Would you want us to write that out on a test?
A lot. You're talking about the multiplicity. Most of the time, the test question will say and state the multiplicity of the 0, and I think your homework textbook does that, and your WebAssign does that. Okay. All right. So we're going to plot our zeros. We have a 0, and we have a -2. A 0 and a -2. All right, let's again talk about the end behavior of the graph. End behavior. This is a third degree. if you tried to multiply all this out, the coefficient in front of the x cubed term is positive. So we know in the end, the graph is going to look like that, right? The end behavior. All right, so that's enough on my graph to already tell me that after 0, this curve is going to have to be going up. And then to the left of -2, the curve's got to be going down. All right, but we're going to double check all this, but we're just trying to analyze and see what's going on, okay? All right, so my little intervals that you would be checking for the signs, the SIGN, is when you're bigger than 0, you're between -2 and 0, and then of course less than -2. Everybody understand how I'm picking my intervals? They're around my zeros. Okay, so let's pick a number bigger than 0, such as 10, and if I put it back in my function, I have a positive times a positive, so this curve's flying off. Okay, what's a nice number between 0 and -2? -1, that's pretty nice. So if I put a -1 in for x, that's negative. What about x plus 2 squared? -1 plus 2 is still positive. Positive squared is positive. So I got a negative times a positive, which is negative. Negative means it's going to come down under here. Uh-oh, look at here. This one crossed the x-axis. This one looks like a turning point. All right, but let's just double check to the left of -2. If you put a -10 in here, you'd have a negative times a positive, which is negative. All right, let's go back to this little definition in your book or whatever it is on page 325. If R is a 0 of even multiplicity, okay, notice that -2 is an even multiplicity. -2 in our example was an even multiplicity. The graph is only going to touch the x-axis at -2, and the y value, the sign of the y value, does not change from one side of R to the other side. So it had to just touch it and go back around. Okay? And there's my illustration. All right, but the end behavior, because it's a third degree, is still opposite directions. All right, last one, and then we're ready to jump on something else, I think. Last example is y equals x plus 2 cubed. Y equals x plus 2 cubed. We already know how to do this one from transformations, but we're going to go through our little steps here. The degree, everybody says third, because if you multiply that out, you have an x cubed term. You know about the end behavior. It's really going to look like y equals x cubed. It's going to do opposite directions. The zeros, we only have one. That 0 is -2 of multiplicity 3. Okay? That is an odd degree multiplicity. Who remembers how that's going to be affected on the graph? Is it going to touch or cross through? It's going to cross. You already knew that. Okay, and the y-intercept. What is the y-intercept? 8. Let x be 0, y is equal to 8. Okay, you know this is just the graph of y equals x cubed shifted horizontally 2 to the left. Okay, so you already knew what it was going to look like anyway, but we're pretending that you didn't. All right, it's going to cross the x-axis at 8. That's all we know from our information here. I mean the y-axis at 8. Thank you. And on the x-axis we have a 0 at -2. All right. Well, if it's got to go through the y-axis at 8, you know the rest of the curve's got to go up somehow like this. Okay? But we're going to pretend at the moment we don't know a whole lot. So our intervals we'd be checking around is bigger than -2 and less than -2. All right, so if you pick a number, well, bigger than -2, of course 0 would be a nice one, so there's our curve going up. Less than -2 might be a number like -10. And I'm looking at the sign, S-I-G-N, is the y value, negative or positive. So when x is -10, you're going to get a -8. -8 cubed is a negative number. So it's going to do exactly what you thought it was going to do. It's going to go like this. Okay? All right, so this is an example where we had only, we didn't have any turning points. We didn't have any turning points. The theorem said you could have at most n minus 1. So we could have 2, 1, or 0 turning points, and this had 0. Is that good? All right, let's flip through the pages, 3.2, look over at the exercises, make sure we're in good shape to go. Let's see, going back, we know how to identify a polynomial function and its degree. We are very good at transformations. We know how to identify the zeros and their multiplicity, if you can factor it. I'm on page 318. And we know how to analyze the graph looking at the end behavior, looking at the sign. All right, flipping through the pages here. We know how to identify a polynomial. The x's have to be, the exponents on the x's have to be 0, 1, 2, 3, 4, 5, 6, 7, whatever. The coefficients are real numbers. We know how to find the degree. It's the term of highest power. We know that polynomial functions are nice smooth curves because it's defined for all values of x. This is not a polynomial in B with little gaps there. We first studied a power function to learn that if the power, which is a one-term polynomial, when the n is even, the ends of the graphs go the same direction. The n is odd, they go opposite directions. The end behavior. Okay, we looked at all that good stuff. We did the transformations. I'm now on page 323. We identified zeros of a function as being your little x-intercepts. If you know a 0, then you know x minus the 0 is a factor. X minus the 0 is a factor. We know about multiplicity, which is at the top of page 324. Multiplicity of the function. When you have x minus r to the m as a factor, talking about zeros of multiplicity. We know a little bit about the graph analysis, whether it touches a graph or crosses through. And then, I don't think I pointed this out to you in the book, maybe I did, I forgot. Page 326, when you're talking about the end behavior, when you have a polynomial function, you actually look at the term of highest power with that coefficient, and you look at that power function. And this just says when you look at this function from a long ways off, you will be able to see the ends looking like the power function. So if your main one is even, both ends go the same direction. If it's odd, they go opposite directions. Okay? And that's all I can tell. In the summary, I just made myself a little note that because this isn't a calculator course, I kind of marked through the number 4 and I say use a sign chart to find when your y values are greater than 0 and when your y values are less than 0, like we just did. Okay? And let's make sure looking at the exercises you're good. On page 331, I think we've already done these. Form a polynomial whose zeros and degrees are given. Let's just do one verbally. If I had a third degree and -2 is a 0, what's a factor? -2 is 0. X plus 2 is a factor. And then x minus 2 and x minus 3. So your polynomial would be y equals a times, we don't have a particular point that's going through. Remember, you can have lots of polynomials with the same zeros, third degree. So it would be y equals a times x plus 2 times x minus 2 times x plus 3. You don't need to multiply all that out. Just
3.
get your factors in there.
Wouldn't it be minus 3?
Minus 3. Sorry. X minus 3. Thanks. Everybody good? All right. And then the next exercise, finding the zeros multiplicity. Does it cross or touch the x-axis? What power function? Okay, this book says, what power function does it resemble? My question on tests usually would be, what's the end behavior? Okay, is it going to resemble? Well, you have to say what power function it resembles. That tells you what your end behavior is. All right, everybody good? I'd say let's do a fun one. Page 332. 332. Let's just jump and do number 94 together. 94. This is a polynomial function. It's a polynomial function. How many zeros do you see there? You see 3 distinct zeros. Do you notice something interesting about the zero number 1 versus the zeros 2 and negative 1?
It bounces, so it's...
All right, 1 is going to touch, and negative 1 and 2 is going to cross through. All right, I see 3 zeros, but I see this one coming around. What would you say, think carefully, would be a minimum degree polynomial that I'd have to have here?
4.
A minimum.
Because actually it could be, when you do a turning point, it's just got to be even through there. So you could have like that raised to the 6th power or whatever. So really it's, and you'll notice your book says there might be more than one possible answer to this problem, but we're just going to work with the minimums that it could be. What would you bet the minimum degree of this polynomial would have to be?
4.
Okay, 1, 2, 3, 4, right? Because that would be, these could be odd, so those could be 1. Zeros of multiplicity 1, because it's passing through. But that would have to be at least a 0 of multiplicity 2. So 1, 2, 3, 4 would be the minimum degree polynomial that it would be, 4th. All right, so let's write what we think the polynomial could be. Everybody got the picture? Let's see if I can bring a blue sheet in here underneath. All right, so this is fun, in case y'all are thinking it's, this is Friday afternoon. That's why I have to remind you this is all fun. All right, so we're going to write a polynomial function. F of x equals, we'll start out with a. All right, and let's start over here with the negative 1. If negative 1 is a 0, what is a factor? X plus 1. Now, because the curve passes through, this exponent on this has to be an odd number. So it could be 1, 3, 5, 7, or 9. Okay, it could be all those. But we're just going to do a minimum that it is for this example. All right, then we're going to get over here to the next 0, which is at 1. So how do we write that factor?
X minus 1.
X minus 1. But because it touches and bounces around, this exponent has to be even. So that could be 2, 4, 6, 8, 10, 100, 1,000, whatever. But we'll just put a square on there to keep it minimum. All right, at 2, it passes through. So what is that factor? X minus 2, and that could be 1, 3, 5, 7, 9, or whatever. We're just going to leave it at 1. All right, so this is the lowest degree that we'd have. Now, can somebody tell me how I could easily determine what A is? Okay, here's a point on the curve. We have the point 0, 1. Whoops, 0, 1. We have a y-intercept shown to us. So we can just put in when y is 1, x is going to be 0. So we have a times 0 plus 1 to the first, 0 minus 1 squared, 0 minus 2. 1 equals a times 1, negative 1 squared, negative 2. we could do this in our head, but again, it's late afternoon already, right? Friday. It's already Friday. Okay, negative 1 squared is positive 1. So 1 times negative 2 is negative 2, so we've got minus 2a. A is equal to negative 1/2. A is equal to negative 1/2. All right, so we have a 4th degree polynomial. We know the ends of the graph are going the same way. We have just found our A to be a negative 1/2. The coefficient in front of x to the 4th is negative. Didn't we expect the ends of the graph to be going down? Mm-hmm. And there we have it right here. Isn't that fun?
Yeah.
The answer to that's yes. All right. We're ready to move on into the next section. And we are going to talk about rational functions. All right. We're in section 3.3 now, and I'm on page 334. And our objectives here are to talk about the domain of a rational function, to identify vertical asymptotes of a rational function, find the horizontal asymptotes of a rational function. In Math 107, oblique asymptotes are not an objective. Okay, so you don't have to worry about oblique asymptotes. But a very calculus-related concept that we want to worry about in this section is limits. So we want to work some more on limits here. Okay, so let's flip to the end of section 3.3, preparing for this section, and see if we're prepared. I'm on page 343. And because of the interest of time, we're going to do this together. 3.3, are you prepared? Okay, number 1, true or false? The quotient of two polynomial expressions. All right, well, we remember what a polynomial expression is. It's a polynomial that's not an equation. So it's not y equals, right? It's just your polynomial. Exponents are on the x are 0, 1, 2, 3, 4, 5. So is a rational expression a quotient of two polynomial expressions? True or false? Say it loud.
True.
True.
True, it is. Okay, remember a rational number is like 2/3, an integer over an integer. A rational expression is a polynomial divided by a polynomial. Polynomial over polynomials. Okay, that's what rational expressions are. Okay, number 2, what is the quotient and remainder when we do a little long division here? So let's do a little long division. It's been a little while since you did a little long division. You don't even remember doing it, right? Okay, we're on page 343. Well, let's just go back to the good old days when we divided something like 2 into 137. And you didn't have a calculator. All right. How did you divide 2 into 137? You went 2 into the 13, right? And you got 6. 6 times 2 is 12. What was the next step?
You subtract down that 1 and then you divide it.
Okay, you had to subtract at this step, right? 13 take away 12, and you got 1, and then you brought down the little 7. I remember my teacher used to make me put little X's under there that you bringing the 7 down so you didn't get lost. Then you say 2 into 17 goes 8. 8 times 2 is 16. And say the next step again.
Negative, minus.
Subtract. And then you usually said remainder 1, or you could go plus a half. Okay? All right, everybody remember that? All right, so the same deal with dividing rational functions. Rational expressions, excuse me. So we have x squared minus 1 into 3x cubed minus 6x squared plus 3x minus 4. All right. Let me write it as the rational expression first. That's 3x cubed minus 6x squared plus 3x minus 4 divided by x squared minus 1. This is my rational expression. The numerator is a polynomial. The denominator is a polynomial. So I have a rational expression. This rational expression is not proper. It is not proper. Who can tell me why this rational expression is not proper?
The denominator.
The degree of the numerator is greater than the degree of the denominator. So when you had a fraction like 6, can't think. When you had a fraction like 6 halves, that was not a proper fraction because you could reduce it. It could be reduced. Or even if you had 7 halves, that was not a proper fraction because it could be simplified to 3.5. It could be simplified further. Okay, so the degree of the numerator is greater than the degree of the denominator. It is not proper. So if you perform long division, you're going to get a proper fraction out of that. Okay, but we need to remember how to divide. All right, so just like you said, 2 into 13, you write your divisor in descending powers of x. What's this thing under here called? Dividend. Good. Your dividend is written in descending powers of your x. So you're going to look at x squared into 3x cubed, and you say, what do I multiply x squared times to give me 3x cubed? And everybody says 3x. All right, so now I'm going to multiply 3x times my divisor and line up similar terms. So 3x times x squared is 3x cubed. 3x times minus 1 is minus 3x. All right, this is the part that people sometimes mess up on. Just like when you did long division before, you then had to subtract. So we're going to subtract here. So that means you're distributing your negative before you add. So you have 3x cubed take away 3x cubed. The whole point was to get that to cancel out. And now you have 3x what? Plus 3x, so that's going to give you a 6x. All right, let's don't forget to bring down our little minus 6x squared. Okay, so now what do you multiply x squared times to give you minus 6x squared?
6.
Negative.
6. So negative 6 times x squared is minus 6x squared. Negative 6 times negative 1 is positive 6. Okay, we don't want to forget to subtract. So don't forget to go through and change your signs. So negative 6x squared plus 6x squared cancel out. That was the whole purpose anyway. And I'll bring down my little 6x. Now what else happened here?
Subtract 6.
All right, you got to subtract 6 from what, that negative 4. Some students tell me that their teachers always want them to bring down everything, every line. So if you wanted to bring that on down here so you didn't lose it. But now we have a negative 4 minus 6 is negative 10. Okay, do I continue on or am I done?
You're not done.
I'm done with my division because the degree of this remainder is less than the degree of my divisor. So we could say plus 6x minus 10 over x squared minus 1. That's my remainder there. Just like I could have said plus a half over there if I wanted to. All right, the degree of my remainder was less than the degree of my divisor, and I knew it was time to quit. Okay? Everybody good? All right. The next part of Are You Prepared? So proper fractions come up in our section on rational functions. Do I have a proper rational function? Meaning, It's proper whenever the degree of the numerator is less than the degree of the denominator. That's when it's proper. Degree of the numerator is less than the degree of the denominator. That little part right there is now proper. Okay? All right. Next example, and we're going to really work this over because we need it for this section. This is number 3, and are you prepared? We want to look at the graph of y equals 1 over x. We already knew how to graph this from our library of functions. Okay, remind me of some key points here. 1, 1. All right, and you kind of memorize the graph look like this. And, right, -1, -1. And the graph looks like this. Okay? All right, so that I can get in a lot of the terms that we're going to look at in the book here, we want to ask some questions. What is the domain? What's the domain? And everybody says all real except what?
0.
X is not equal to 0. All right, we looked at that denominator to know what our domain was. All right, we want to add to this the vertical asymptote. A vertical asymptote is a vertical line that the curve approaches and the curve heads in the direction of positive infinity or negative infinity. When you have a rational function that is proper, what does that mean?
The numerator is less than the denominator.
You're so good. All right, so, and I'm going to go back with other illustrations, but I'm just going to work this one over right now. So this one is proper because the degree of the numerator is 0 and the degree of the denominator is 1. Okay. When you have a rational function that is proper, it's very easy to find the vertical asymptote. It is where the function is undefined. So my vertical asymptote is the line x equal to 0, which is the y-axis. Okay? Now, I'm going to push you into the concept of limits, and I'm going to come back and redo all this stuff with more things that are in the book, but I'm working this over. If I say, what is the limit as x approaches 1, but I want to be just a little bit to the right of 1. I put a little plus by that 1. That says a hair bigger, 0. Sorry, I want to get around that asymptote. X approaches 0 from the right, just a hair bigger than 0. What does the y value of 1 over x approach? Okay, so here is x at 0. A hair bigger, that little plus means just a little bit bigger. You know, like when you're on your number line, plus goes to the right and minus goes to the left. Okay? So if you're just a little bit bigger than 0, you're over here. So when you're over here, where is the y value headed? Everybody says plus infinity. Okay? How do you bet I write it if I want to be just a hair smaller than 0?
0
Limit as x approaches 0, and what kind of little symbol would I use here, do you bet, if I'm a little bit smaller? A little minus. That means take just a hair away from 0. Subtract just a little bit from 0. Little bit. And tell me where the y value is headed. So a little bit smaller than 0 would be on this side. And where's the y value headed? Negative infinity. Okay, definition of vertical asymptote. You look what makes the denominator equal to 0. And as you approach that from the right side of that number or the left side is coming from the negative part, right side is from the positive part. if your curve flies off to positive infinity or goes down to negative infinity, x equal to 0 is your vertical asymptote. Definition of vertical asymptote. It just means you have a line, and as you get close to that line, the curve flies off to infinity or goes down to negative infinity. Okay? Vertical asymptote. You usually just find those very easily. You have a rational function, reduce to lowest terms, where whatever makes that denominator 0 is it. Okay? All right. Next word I want to talk to you about is horizontal asymptote. Horizontal asymptote. Well, horizontal we know is a horizontal line. Okay, the definition of a horizontal line. As x gets really, really big, or x gets really, really small, what does the y value get very close to? So let's just do a visual here. As x gets really, really big, what is this y value getting really close to?
0.
Y is getting very close to 0, correct? And as x gets really, really small, what is this y value getting close to? 0. So because x is getting, as x gets real big or x gets real small, the y value gets close to 0, we would say y equal to 0 is our horizontal asymptote. Okay, this is the way it goes. The limit as x gets really big. What symbol do we use for really big?
Infinity.
Infinity of 1 over x. This says as x gets really, really big, what does the y value 1 over x gets close to? And that is 0. Y gets close to 0. Therefore, definition of horizontal asymptote, y equal to 0, right here, this is y equal to 0 is my horizontal asymptote. We can look at the limit as x gets really, really small. And it's approaching 0. 0 is my horizontal asymptote. Definition of horizontal asymptote. Okay? Now, we have a little theorem in here that they want you to memorize. But I'm going to tell you what it is right now. This theorem, by the way, is on page 343. Theorem on page 343. I'll come back to this in a second. But whenever you have a proper rational function, meaning the degree of the numerator is less than the degree of the denominator, the degree of the numerator is less than the degree of the denominator, you will always have y equal to 0 as a horizontal asymptote. In that case only. Whenever the degree of the numerator is less than the degree of the denominator, always y equal to 0 will be a horizontal asymptote.
When the numerator is
Degree in the top is less than degree in the bottom.
less.
Less. Proper. Whenever it's proper, y equal to 0 would be a horizontal asymptote. Okay? All right. So we're ready to have some fun, right? Let's have some fun. All right, let's start out with, we're going to start out with, again, a problem. Now let's do one we don't know how to do. Let's look at f of x equals, let's start out with just f of x equals 1 over x squared, and then we'll build on this rational function. This is a rational function. The numerator is a polynomial of what degree? What's the degree of that numerator? 0. What's the degree of the denominator? 2. Both of these are polynomials. Therefore, a polynomial divided by a polynomial makes a rational function. Okay, we've got a rational function here. All right, let's see what we can do about this. What is my domain here?
All the numbers.
Domain is all reals except what?
X can't equal.
X cannot equal 0. I've got division by 0 here. Now this rational function is reduced to lowest terms. It's reduced to lowest terms. There's no factors that simplify out. Right now I haven't shown you one that does, but I will eventually. All right. Because this thing is proper, can you tell me the vertical asymptote? x equal to 0. It came right from looking at that domain. So x equal to 0 is your vertical asymptote. Okay. Now, let's think about it. Let's look as x approaches 0 from the right, a little bit bigger than 0, of 1 over x squared. And let's look at the limit as x approaches 0, a little bit smaller, of 1 over x squared. Now we know when we're getting around that horizontal asymptote, the curve's got to fly off to positive infinity or it's going to go down to negative infinity. It's like a brick wall. You can not pass through, you cannot cross a vertical asymptote because your function's undefined there. It's not even defined there. Does that make sense? So there's your brick wall. It's like you got a hose spraying on the wall. The water's either going to go up or down. Sometimes it goes both ways, but really it's a function, so it can only go one way. All right, so if you're a little bit bigger than 0, I like to put in little checkpoints like 0.1. If you put a 0.1 in and square it, isn't that a positive value for y? Positive value for y. So what would you say the curve's going to do when it starts getting here? Is it going to fly up or is it going to fly down? You got a positive y value. Where's it going? Up. So you say it's going to go in the direction of positive infinity. 1/10, 1 over 1/10 square is 1 over 1/100th, which is 100. If you let x be 100th and you square it, by the time you flip it over, you got a big number. Does that make sense? So the curve's going to be going up like this. A little number smaller than 0 would be like negative 0.1. You're over here. But what happens when you put that in there and square it? It's still positive. So that's headed in the direction of positive infinity. Well, if you think about it, 1 over x squared, can that thing ever be negative? No, it's always positive. 1 over something squared, 1 over a positive number is always positive. So our entire graph is going to be up above the x-axis. Doesn't that make sense? All right, and clearly we already know that the point 1,1 is on here. How did I know that? I just plugged and chugged, right? And negative 1, 1 is also on here. All right, now let's check out what we think about a horizontal asymptote. A horizontal asymptote says as x gets really, really big, what does the y value get really, really close to? As x gets really, really big. Well, just put in a number like 100 and think of this in terms of food, this part of a pie. 1 over 100 squared, that's 1 over 10,000, and you only got 1/10,000th of a piece of pie. You're not getting very much, are you?
Close to 0.
It's getting very close to 0. Because 1 over a huge number, and I'll just back up, like 1/10, think of food, 1/10 of a piece of pie, 100th of a piece of pie, 1,000th of a piece of pie. You're down to the crumb range now. 1/1,000,000th of a little piece of pie to eat, you're not getting much to eat. It goes in the direction of 0. Okay? So we know that we have a horizontal asymptote. Horizontal asymptote is y equal to 0. And we can also look at the limit as x approaches negative infinity of 1 over x squared. Well, the thing is going to be that when you square a negative, you get a positive. So you're still getting numbers like 1 over 100, 1 over 10,000, 1 over 1,000,000. That is getting very, very close to 0. So by definition, you have your little horizontal asymptote here. Somebody want to tell me what the graph of y equals 1 over x squared is going to look like? It's going to come right here and then approach the x-axis. And it's going to come like this and approach the x-axis. Correct? Mm-hmm. And you could also plot some points in here just to verify that for you, and I think your textbook probably did do that for you. All right. We did not get very far at all in section 3.3. There's lots of fun things to do, But you can already start. I'm looking at the exercises on page 344. It asks you to state domains of rational functions. It asks you in these exercises to visually tell what a vertical asymptote is, a horizontal asymptote. Oblique is not an objective. I hope that's not in your WebAssign. And then we'll pick up with the curve sketching next time. And next time we need to cover a couple more sections in the book. All right, have a great day, everybody.